Do we have Peter? Peter, tell us why BGP is the better IGP.
That's it, right? So thanks everybody for coming, and thanks to the committee for picking up our talk. Today we're going to talk about our experience with data center design and use of BGP as the only protocol for the data center routing. So before we begin, let's quickly look at the structure of this talk. So I'm going to start with the problem statement, talk about our data centers, our challenges, then outline our first design, which was done a few years ago. We're going to talk about why we chose BGP over more conventional protocols such as OSPF or SIS. And finally, we're going to talk about our new approach we're using right now for new deployments. So let's have a look at our data center specifics. So we run online services, and online services is everything which services customers over the internet and has over millions of active users at every time. So we do run a lot of servers on the scale of hundreds of thousands in our data centers. And these servers utilize mostly 10G and 1G NICs. I can't say they're all 10G right now. There's still a lot of 1G, but 10G NICs were a major driver for higher capacity and higher bandwidth. So all the applications we run are kind of specific. So the applications are well aware of a network. They're designed to be run on the network, and we treat the network as a computer. So essentially, the application is well aware of topology and utilizes full capacity and full capabilities of a network to perform computations. In other words, the applications are parallel and specialized to perform just, say, one function, such as web index computation, or, say, service an email, service a mailbox of the internet. And so this is quite different from traditional enterprise, of course, and this brings some specifics to design and application behavior. So most important part is, I believe, like Andy mentioned before, is a specific type of traffic flows that we have. So there's all the specifics, but in very simple fashion, you can divide the traffic flows into queries and background traffic. So queries is what customers send you, or what applications send to each other to perform, say, calls or some requests. And background traffic is the majority of all traffic that does all the work, such as web index computation or mailbox moves and all those things. And background is the majority of all traffic in our data centers. It's a heavy bulk flow, and they run from server to server. Or in other words, like we call in the industry, they run east-west. So the challenge was twofold. First, to find topology which is simple enough but provides enough capacity from server to server, at the same time allowing us to keep the design very simple and uniform. And secondly, we had to pick up a routing protocol that allows us to use single solution for data center everywhere, the protocol which has as simple behavior as possible, and the protocol which has a very wide vendor support. So the last requirement is specific because we often tend to change our vendors for the purpose of driving costs down. So in order to keep the solution working, we need a protocol which has very wide interop and support from every vendor. So let's look at our first initial solution. So the choice of Clos topology, I guess, is now very common in the industry. So Clos, as they call in the industry, is a network which has 3 stages. the middle stage is often called spine layer, and the input and output stages are often being folded together and being called as a leaf layer. So the Clos may have multiple stages. Normally it's having 3 stages, but you can actually grow with topology and have 5, 7, and more stages. The only problem is that as you grow the Clos topology, you also increase the complexity of the link structure. So this topology provides full bisection bandwidth as long as your number of uplinks, M, from the leaf switch is more or equal to a number of downlinks going down to your, say, top of rack or end of row switches. We use top of rack only, so this is why you see top of rack layer on the diagram. So our initial design was exactly a Clos topology, which had from, say, anywhere from 8 to 30 switches in the spine layer, and which connects our containers, because we mostly use container deployments in the data centers, and links them into a single fabric inside data center. So we deploy leaf switches in pairs, so this way we can use multi-chassis link aggregation, or mLAGs, to increase capacity or bandwidth inside the container. So as you can see, initial design has layer 2 inside the container. So the reason for this was mostly to have compatibility with our old designs, because our old designs were based on layer 2 topologies mostly. And as you can see, mLAGs have been chosen as a solution to aggregate capacity inside the pod sets or containers, as we call them. Also, one specific is oversubscription is only done at the top of rack layer. This way, you can treat the topology as a single bandwidth domain over the top of rack. Or in other words, when you talk to the application guys, you can tell them you have full capacity in the rack, and out of the rack you have this oversubscription ratio. So for the routing, after a lot of discussions, we chose to use BGP only as a routing protocol. So as you can see, we have a single S number, single S for the spine, for all spine devices, and then a single S number for every container. So essentially, on the leaf switches, you simply advertise the leaf VLANs into BGP, and you use equal cost multipath for load sharing across the links in the topology. So the spine width is normally from 8 to 32 switches, like I said, and this means we require a vendor to support this large fan-out for equal cost multipath, both on the leaf and spine layers of this topology. So probably this is the main question, why we chose BGP over more conventional protocols such as OSPF or ISIS. So first of all, the main argument was simplicity of BGP, because if you look at BGP specification and source code, you can see the state machines and data structures in BGP are much simpler compared to, say, OSPF. If you simply compare OSPF adjacency formation process with BGP update exchange, you can clearly see that BGP is much simpler. Of course, like some downsides, because some implementations of BGP put too much efforts into optimization, specifically into update taking process, and we've seen some vendors having issues and bugs in specifically update taking process. But in general, our experience in testing and operations was that BGP deployments are much simpler to operate and support. And secondly, probably our very important feature is BGP being essentially a protocol which is distance vector, allows you to change routing behavior hop by hop basis. So essentially, in our deployments, we use this to do some sort of simple traffic engineering. We can peer with every device using multi-hop session and inject routing information at every hop. And this way, perform some sort of very simple, crude, but actually efficient traffic engineering. So secondly, trying to troubleshoot BGP is generally more simple. Basically because BGP has just single RIP, local RIP table, and if you take OSPF or ISIS, you have links to database, which has to be translated into the routing table using SPF calculations. So normally, BGP is, say, more explicit in this sense, because what you see basically is, most often is what you get in routing table. Plus, you can always see which routes you receive and which routes you send to your neighbors. Whenever, say, in OSPF, you have to look at the flood lists and links being sent to your neighbors. And overall, trying to troubleshoot OSPF is generally more difficult. Of course, there are some downsides again. Let's say, for example, OSPF may allow you to find MTU issue actually before you run into any problems. BGP will form adjacency or actual peering session even if MTU actually mismatch, because TCP will actually perform MTU discovery and you'll never find out an MTU problem. However, in our environment, we do have very tight control of all the switches and the network, so we can always ensure that the MTU size is uniform everywhere. So the last argument, event propagation or event flooding in BGP is more constrained. Since BGP is distance vector, a change in the topology will normally stop at some point of hierarchy. Let's say if a link flaps in OSPF, the event floods the whole area, no matter where it happens. In BGP, normally, once you find different best path, you stop flooding the event and just converge on a new path. So in general, we found that under specific failure scenarios, BGP has better fault isolation. So there are two main common arguments against BGP. The first one is that configuring BGP is much more complex than, say, compared to a link state protocol. You have to set up all the neighbors, AS numbers, possibly BGP policies on the peering sessions. But in our environment, we have this all done automatically by using config generation. And there is no complex policies, just peering sessions and AS numbers. Nothing special. So this wasn't actually a problem for our deployments. And for the convergence time, which is BGP's main problem on the internet, hasn't been an issue for us, mostly because we have very simple and symmetric topology. Essentially, it's a Clos, all links are uniform, all paths are uniform. If something fails, analysis and simulations and experience shows that it takes only a few seconds to reconverge. And probably the biggest feature which contributes here is that all links are point-to-point, and it's all fiber. There's no converters, so once a link fails, most BGP implementations shut down BGP session, and the network performs restoration of from a failure almost instantly. So our experience has been that practically any failure has been healed within like maybe less than a second. And even if it takes, say, 5 to 6 seconds, our environment can tolerate this issue with no problems. So there have been some problems with this old approach. So first of all, as you can see, we still had layer 2 in the container. And this, of course, had a lot of problems, mostly broadcast terms, unicast terms, mLAG issues, because all mLAG implementations are proprietary, and as you change your vendor, you get new issues with every new implementation. So mLAG is a, let's say, nice feature, but since it's so non-standard, you always encounter some issues. I guess almost everyone has this experience. Secondly, having just single layer spine devices limits scalability of the capacity data center. So the only way you can scale single spine is by adding more line cards or more port density in the spine boxes, which somewhat limits purchase of vendors, because there are vendors who have some really nice spine devices, but say if you have to change a vendor for the cost reasons, you actually limit yourself by logging into chassis boxes with large port densities. So one of the reasons was, let's try to get to simpler boxes with lower port densities, but just try to scale the spine not up, but horizontally. And lastly, mLAGs only limit us to 2 devices, 2 switches in the container. So essentially, the same problem. We have to grow capacity up and can scale horizontally. So the new design was, let's pick up our Clos topology and create multiple parallel Clos topologies instead. So let's say on this diagram, you see 2 Clos topologies, green and red. And every Tor switch, top of rack switch, has an uplink to every Clos topology. So right now you double your capacity by having 2 parallel topologies. So in other words, this is actually the same Clos topology, but now having 5 stages. So if you count stages from the Tor to the spine and then down again, you'll see there are actual 5 stages to cross from Tor to Tor. So this new topology allows you to scale horizontally by adding more and more parallel designs or parallel topologies. So you no longer depend on having high port densities in your, say, spine switches to scale the capacity. And the next problem was fitting our BGP design into this new topology. So since our main intent was to get rid of layer 2 in the container, we went ahead and pushed BGP all the way down to the top of rack switch. So as you can see in this topology, every top of rack switch has a separate ASN number. So effectively, every top of rack is a small BGP device in its own AS. So we allocate a single AS per row of leaf devices in every container. And the spine, once again, all parallel spines in this topology have the same AS number. So 2 biggest benefits is L3 down to the Tor and the use of BGP, the same protocol we used before for routing. Of course, our biggest win was we no longer have any L2 issues because majority of our support and operational issues have been tied to broadcast terms, unicast terms, anything which is specific to Ethernet. And now we can grow capacity horizontally by simply adding more and more boxes in the spine or a leaf layer. You can increase capacity, how much you want. Of course, with a downside, because by adding more switches, you also increase the link density. And so this is probably the main challenge, trying to manage that many links in this topology, especially handling the link errors. But we do still have same protocol everywhere. It's still BGP, and there is no requirements to do any redistribution or interworking, just single protocol everywhere. And lastly, BGP has some nice properties. Specifically, the OSPF attribute allows you to see the exact path your prefix took in the topology. And this also helps in troubleshooting, because you can know, hey, this prefix came from that Tor switch in that container. So we don't have time to go over all specifics of this design. There's a lot of tips and tricks here and there to optimize BGP and this design. So we only cover a few most important issues we found in this design. So first of all, we need to support a feature known as a BGP multi-path relax. It's not very widely used. Some people know about this, some people don't. The requirement for this feature is specifically to allow equal cost multipath across paths which have different OSPF attribute contents. The same OSPF length, but different contents. Normally, BGP doesn't do load sharing across these paths. But we need this to implement our load balancing over any cast prefixes. So this was the first requirement to vendors, and not all vendors support this functionality. But I guess right now most of them actually do. Secondly, we had to use 16-bit ASNs, and we had to rely on the private AS numbers. The main requirement for private AS numbers is that we can use that for simplified filtering at the edge, and we can use the remove private AS feature on the data center edge to easily strip all the information about data center routes. So in other words, this helps to implement edge routing policies. But the downside, we only have 1,000 private AS numbers, and the number of Tor switches often exceeds 1,000, I mean, maybe 2 or 3 folds. So the question was, how can we handle, how can we use private AS numbers in this topology without getting into any black hole routing issues? So the solution was another pretty old and well-known functionality known as allow AS in, which permits a BGP speaker to accept his own AS number again. So we apply this feature on our Tor switches on the uplink sessions to the leaves, and we reuse the same BGP AS numbers inside the containers. So essentially, let's say in every container with AS numbers 1, 2, 3, 4, and 1, 2, 3, 4 again, and so on and so forth. Something like that. Once again, this functionality is not very, I'd say, uniformly supported by all vendors. Let's say Cisco has been changing this a few times. So first it wasn't there, then it wasn't again. It's different from AnnexOS to Cisco iOS and iOS XR. But we managed to get most vendors to support this functionality properly. So basically, this is like a short message to the vendors. If anyone's listening, we only require a few very simple features to make the design works. And most people have those. Some people don't have them implemented properly, but it's not very hard to implement this functionality in BGP. Those are all very simple features to support. We only have a few minutes left, but let me point out about a few very specific design features what we ran into. So first of all, you cannot do summarization in this design. In other words, you cannot summarize server subnets. The reason is, if you do this, you can easily run into black hole scenarios. Let's take the first specific summarization case, default routing. Let's say your leaf switches only send default route to the Tor switches. Say in our case, A and B send default route only to the Tor switches to improve scalability and reduce table sizes. What's going to happen if a link from A to D fails? The switch C will never know about that and keep sending traffic to both A and B leaf switches. And this will create black hole for traffic going from switch C to switch D. So the only way to avoid this is by not using summarization from the upper layers to bottom layers. And the same problem applies when you try to summarize server subnets. Let's say you pick up leaf switches A and B and summarize the subnets on C and D into one range. And once again, this creates a black hole scenario where switch B may lose connection to switch C, but still advertise the summary range. In traditional designs, people solve this by creating the peer links between the leaf switches, for example. The problem here is that the number of leaf switches is growing. When you have 2 devices, you're fine with that. When you have 4 devices, you have to use more links to create this full peer mesh. When you have 16 devices, it's almost impossible to create this peer mesh across all devices to support backup routing in case of failure. So this might be a scaling limitation, but in our case, the switches we use and the scale we operate at is pretty consistent, and we only use maybe about 40%, 50% of full fib size in every switch in the network. So we found out we don't really need to summarize, and if we need to, we can only summarize the point-to-point links, which doesn't create any issues. All right, so the quick summary. Traditional perception of BGP was that BGP only suitable for large-scale deployments and internet routing. But what we found out, in data center, it works perfectly as an IGP, a single protocol for all routing problems. So BGP is simple enough. It supports per hop traffic engineering, and it's being implemented and supported by basically all vendors we know. And so this all together made this protocol probably the best choice for us. And this is why we're using it in our data centers. Thank you. Any questions?
Thanks. Thank you.
Yes.
Okay, so we are over a little bit on time on break. We're going to try to come back on time, though. Real quick, we do have a survey winner from the surveys yesterday. Is Hans Adelman in the room? Go to the back table to collect an iPod Touch. And for the rest of the giveaways for the rest of the week, we have another iPod Touch and a pair of noise-canceling